Hello students, in this video we're going to revisit solutions for a little bit and use that to introduce the concept of molarity and dilution. So let's get through this quickly, make as short a video as possible. So when we're talking about solutions, let me just remind you that there's two components to a solution. We have the solvent. Remember, the solvent is the larger component. And that the solvent is going to be what disperses the solute. For example, if we put salt in water, sodium chloride in water, the water molecules are going to interact through ion dipole forces, and they're going to separate the sodiums and the chlorides as much as they can, get them as far apart from each other as possible. So the solvent is sort of the medium that does all the work. The solute is the smaller component. Now, I'm sure if you got online, you could look up some exceptions to this, but we're dealing in generalities here. So the smaller component, and just to keep it simple here, we'll say the solute is the one that gets dissolved. So back to our illustration of the sodium chloride in water, then the sodium chloride would be the solute. It's the one that gets kind of broken up and spread around evenly all over the place. Okay, so now we're talking about solute, which is some substance dissolved and dispersed in water. And now we have two more words, two vocab words that we did before spring break to help us talk about how much solute is actually there. So concentrated means basically that you have lots of solute. Lots of ions, lots of molecules if it's covalent. You just have lots of solute, and I'll put this little disclaimer here, per amount of solvent. So since the word lots is relative, we have to have something to kind of compare it to. So when we talk about concentrated solutions, there's lots of solute in ratio or in comparison to the amount of solvent particles there in some way, and I'll show you that here in a minute. There's lots of ways to do this. Now when we say something is dilute, that means then that's the opposite of concentrated, and then you have few solute particles. And then I'll put the disclaimer there again, per amount of solvent. So very, very similar to what maybe some terms you learned in human geography. If you have a high population density, people are really concentrated, they live very close by, very near each other. And then rural areas that don't have a lot of population will be something like this dilute. You don't have very many people in that area. So similar terms, just used in different applications. Now how do we measure concentration? Since the word concentration will envelop all of this, both dilute and concentrated, well, we've got lots of different ways. We have something called a mole fraction that we could use. That's just the moles of your solute over the entire number of moles of everything, including the solvent. You can use part per million or part per billion. You probably have seen those units somewhere in your reading, if not in class. You can do a mass percent. So you take the mass of the solute over the entire mass of the solution, everything, and get a percent out of it. And you could also do a volume percent. Same idea. You take the volume of the solute over the volume of everything in the solution, and that's most useful for liquids. And then some more, I guess, application specific ones. Here's one that we're not going to do very much of, molality. It has an application for what we call colligative properties, and so those are kind of a standalone unit. We don't do those every year, but molality is moles of solute over kilograms of solvent, so a little bit different type of thing. But the one I really want to focus on is the one we're going to learn this year, molarity. I know those two words look the same, but molarity, we'll just go to the next page here, is defined as moles of solute per liters of solution. Now that's more than just a formula. Yes, it is a formula, but it's more than just that. It's also a definition. And what I mean by that is if you use the molarity quote-unquote equation, which is this definition, moles over liters, then when you read a word problem and you try to plug in words to solve for any part of this, you have to plug in liters. It is a liters specific definition of molarity. So typically this is the form we use when we solve problems. I'll do some examples here in a moment and you'll see that. But before we do that, I just kind of wanted to get into some rearrangement here. This liters is just a volume. So I just rewrote this equation by putting volume instead of liters, just generic volume. And then I rearranged it. I multiplied molarity times volume down here. And I wanted to show you that that still equals moles. And that's important because when we make dilutions, okay, remember I said on the previous page, something dilute means few particles. That is an adjective, but I can actually turn the word dilute into a verb. I can dilute something by adding more solvent, which is usually water. So to dilute it, you're just going to add additional water. Again, it's almost everything we do in here in pre-AP is going to be aqueous, so our solvent's almost always water. So what we do by adding water is we change the volume of the solution while the solute stays exactly the same. So think about that. The solute stays the same. Molarity is moles of solute per volume, which is changing. So if I think about this, the moles are constant. So if I have the moles of a solution before I add water to it to dilute it, then after I add the water, the moles are still constant. I just add water. Nothing else has changed. And now from this relationship here, I can sub in the molarity times the volume before I add the water, we'll call it concentrated, will equal the molarity times the volume after I add the water, which is now dilute. So this little relationship here should look familiar to you. It sets up exactly the same as Boyle's law from the gas laws. You have an inverse proportion between molarity and volume. As the volume goes up, like we see here, V2 is greater than V1, so we've increased the volume. Volume goes up, and we see the molarity goes down. In other words, we've diluted the solution. So this little proportion here, which is all it really is, because we're just changing the water, is another little dandy equation to use along with molarity. Alright, let's put that aside and let's actually do some problems now with molarity. Alright, get out my calculator and my pen and let's get going with this. Alright, I'm not going to work every problem on this sheet. I'm going to pick and choose and just give you a good head start on learning how to work these. We'll start with number 2. We want to find the molarity of a salt solution. We've got 50 grams of sodium chloride and 750 mils of water. Alright, so the first things first is, I told you in the molarity equation that we will not be dealing with milliliters, it's got to be liters. So I'm going to move my decimal 3 places to the left and turn that into 0.75 liters for my volume. Next, what I've got to do is get 50 grams of sodium chloride, and by the way, this worksheet has just absolutely no consideration for sig fig, so don't even worry about it. So 1 mole over 58.5 grams. So that 58.5 is my molar mass of sodium chloride. For those of you who might want to see that, I'll include my work. 58.5. All right. So that's going to give me moles of solute. If I did my math correctly, which is questionable nowadays, 0.85 moles. Okay, that's not our answer. That's just the moles of solute. Now to find the molarity, we're going to use moles per liter. 0.85 moles over my 0.75 liters. So this solution has a concentration of 1.14 molar. That's a capital M, and the abbreviation is molar, like the tooth. That's how we say it. 1.14 molar. All right. I'll just run through number 3 here so you can see it twice. We've got 1.2 kilograms of KCl. All right, we're going to turn this into moles. I'm not going to blow your mind here, so let's just do a quick conversion. Let's move that decimal place 3 places to the right. That's 1,200 grams. All right, now let's very quickly convert that into moles. So 1 mole of KCl. Let's do the molar mass in our head here. I think K is about 39 and Cl is 35.5, so I believe that's 74.6. You can double check using the periodic table after the video is over. But once again, if I did my math correctly, that's 16 moles. Not 60, 16 moles. So the molarity here should be an easy calculation. 16 moles of solute, that's a lot, divided by 12 liters, which is also a lot. So that only comes down to 1.3 molar. Usually anything over 1 we would consider fairly concentrated. All right, let's skip number 4 for the sake of time here. Let's look at 5 and 6 just to solve for some different things here. So in number 5, I've got a 10 molar solution of hydrochloric acid. It takes up 650 mils. How many moles of HCl are dissolved? And then it asks for grams. So the one I want to focus on, we'll do both, but I want to focus on this part. So we're going to solve for moles instead of molarity this time. So in our equation, we've got 10 molar, and that equals, we're going to solve for moles. I'll just make moles my variable just to help you in the video. And then again, convert milliliters 3 places to the left, 0.65 liters. All right, so cross multiply to solve those. And so the moles that I calculate here will be 6.5 moles of HCl. So that answers part A. 6.5 moles. Really easy when you're solving for moles. All right, it did ask for grams, so just for completion's sake, let's go ahead and convert those moles into grams. So 1 mole of HCl is 36.5 grams. That comes from 1 plus 35.5. All right, I got 240 grams. Definitely can stop and check the math if you want to. All right, number 6. Let's go quickly here. Number 6 is going to be the one that students miss the most. This is the one where we get algebra fail. Let's look and see what we have to do. 0.5 molar solution. I have 2 moles of H2SO4. What is the volume? So if we look at the molarity equation, the volume is in the bottom. And when that becomes your variable, this is where students get in a hurry with algebra and miss the problem. So let's set this up. We've got a 0.5 molar solution. I've got 2 moles of H2SO4, and I'm solving for the liters. Or you can make it X, or you can make it V, whatever you want to do. So let's go through the algebra. I'm going to cross multiply. So 0.5L equals 2. And so L will equal 2 over 0.5, which is 4 liters. So it's real easy if you just follow the algebra rules. What most students do is either divide 0.5 by 2 and leave L in the bottom, or they divide 2 by 0.5 and still leave L in the bottom. So make sure you do that initial cross multiplication when you're variable. You did this before. This is the same algebra we saw with Charles's law, Gay-Lussac, Avogadro's back in gas law. So just be careful with it. Okay, on these last few problems here, we're going to do some dilution stuff. So we're going to move away from the moles over liters, and we're going to get back into the M1V1 equals M2V2. We're going to do dilution. So I have a stock solution of HCl that's 12 molars. So a stock solution is just like what your teacher would have in the chemical room, the stuff we order from the company that's concentrated. All right, so that's an important idea. Stock means concentrated. It's like when you go to the grocery store and you buy the orange juice or lemonade and it comes in the frozen cans. That's concentrate. You take it home, you open it up, you add water to get it to the strength you want. Anyway, it's 12 molar. How many milliliters of the stock solution would I need in order to make 50 milliliters of a 2 molar solution? So let's think about what we're trying to do. I have a very strong 12 molar solution, and I'm trying to water it down to get to a 2 molar solution. So I'm adding water. After I do that, it's going to be 50 mils. Okay, so that's what my dilute solution is going to be. So I'm going to have 50 mils of a 2 molar solution. Alright, so remember, it's coming from a 12 molar solution, and the question says, well, how much volume of that do you need? So the math here is not too hard. We're going to divide both sides by 12 molar, and V1 is going to equal 8.3 milliliters. So if you're thinking, let's put this into some context here, and let's make it more than just a number we calculated. So let's pretend that your teacher is making this solution for you to use in lab. This is the one your lab instructions say to use. 50 mils of a 2 molar solution of hydrochloric acid. Well, as teachers, we don't have 2 molar solution in the chemical room. We buy it from the company at 12. That saves money on shipping. We're not paying for extra water. We buy it concentrated. So what your teacher's going to do is go back to that 12 molar solution in the chemical room. Your teacher's going to measure out 8.3 milliliters of it. That's the concentrated stuff. And inside this 8.3 milliliters is all the moles that you're going to need for the reaction. Right? It contains all the moles. So then you put this 8.3 mils into a beaker or a volumetric flask or whatever you're going to mix it with. And then you're very carefully going to measure out how much water. How much water are you going to mix with this? Think about that. You're going to add 50 minus 8.3. So what is that? 41.7. You're going to add 41.7 milliliters of water to this concentrated solution, and that turns the volume to 50. And now the moles are more spread out. The particles are more spread out. So that's what a dilution does. Let's do another quick one here. Number 8, if I dilute 5 mils of a 6 molar acid. So we've got a 6 molar acid, and I have 5 mils of it. Okay, that'd be 30 mole. Well, no, it wouldn't. It would be 0.03 moles, I think. And we're going to add water to it until the molarity drops to 0.5. Okay, so how much solution would that be at that point? It didn't ask how much water we're going to add. It said how much final volume would it be? How much would the solution have? So we do our easy math here. 6 times 5 divided by 0.5. That's 60 milliliters. So to dilute this thing from 6 to 0.5, I have to increase the volume of the entire solution to 60. How much water did I add? If you're thinking 55 mils, you're thinking right. I had to add 55 mils of water to get the final volume to be 60. Okay, so let me address a question you've probably developed now that you've seen me work these two problems. Sorry about the crooked paper there, I didn't notice that. But the question you may be wondering right now is, how am I using milliliters in my equation? Because I went through some effort up here in using the molarity equation to tell you that it had to be in liters. And that's true, I didn't lie to you. When you use this equation up here, molarity equals moles over liters, it has to be in liters. It has to, that's the definition. But down here in this dilution stuff, we're not plugging into a definition. We're just using a ratio, like the gas laws. Okay, so remember how it didn't matter for the gas laws as long as your units match. These are just proportions, so as long as your milliliters on both sides or molarity on both sides, you're good to go. You don't have to worry about that. Alright, I won't stop the video there. If you have any questions, make sure to reach out and get those questions answered. Molarity is a very important unit in chemistry. As you move into AP chemistry, almost everything we do involves molarity. It becomes like the most important unit in AP chemistry. So do reach out if you have any questions. I hope you learned something.